This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
In physical space, a quantum state can warp, twist, and deform continuously without tearing its underlying structure. Even under extreme geometric pressure, the object's core identity remains perfectly intact. Classical topological quantum field theory, or TQFT, defines this behavior through the Atiyah-Segal axioms. It operates as a strict mathematical functor, mapping n-dimensional physical cobordisms, the geometries evolving over time, directly into vector spaces. This creates a bridge between two very different mathematical worlds. You have the smooth, continuous nature of physical geometry on one side, mapped directly to the rigid, discrete logic of finite-dimensional vector states on the other. Under this framework, any two equivalent physical deformations will always produce the exact same vector space transformations. It guarantees that topological invariance holds true regardless of spatial manipulation. This mathematical mapping works flawlessly for standard particles and matter, but that success relies entirely on the built-in constraints of mass, energy, and the strict finite dimensions of physical reality. Remove those physical boundaries, and the equations break down. Standard physical mathematics lacks the convergence controls necessary to handle infinite recursion and limitless scaling. Digital architectures do not have mass or physical limits. Without those physical constraints, a massive network out to absolute infinity. To model boundless abstract systems, we use an extended functor. We mathematically abstract continuous physical manifolds into discrete digital state systems. The mapping target changes, moving away from dynamic linear transformations to collapse the state into a purely static, isolated space, the invariant category. Inside this discrete category, no non-trivial morphisms exist. Once a network's mathematical identity is mapped into the space, it cannot legally transform into a different identity. To enforce this static identity across a dynamic, Turing-complete computer network, we have to artificially bound the environment. We install 4 specific mathematical operators to stop the system from scaling into divergence. Abstracting physical topology into these rigid computational invariants provides a mathematically sound method for proving that a decentralized software network retains its exact architecture, no matter how many times it updates or evolves. As a decentralized network expands, it risks structural drift. Adding millions of new nodes often dilutes the original logic and corrupts the structural equivalence of the system. We counter this drift with the fractal operator. This function rigorously decomposes a massive system state into self-similar subcomponents. You can tunnel downward infinitely into the network's recursive layers, and the exact mathematical architecture of the original root system remains preserved at every single depth. This means distributed protocols, like decentralized storage networks or autonomous organizations, can safely shard their operational logic down to a solitary, isolated node without sacrificing systemic integrity. Exploding a network's architecture into millions of fractal pieces algebraically preserves the exact same topological invariance as scanning and auditing the entire global system. Infinite computational subdivision is safe because the microscopic digital nodes natively inherit the exact security rules and structural stability of the macro network above them. The next major threat to digital systems is participation scale. Traditional linear aggregation models break down when participation is unrestricted, pushing tokenomic stability toward infinity. This chart shows an infinite sequence of network node contributions rapidly stacking upward toward infinity. To resolve this paradox, we apply an analytic regularization tool called the Zeta aggregation operator. By applying an exponential decay factor, we severely throttle the mathematical influence of the network's long tail. This mechanism relies on absolute convergence. Even if millions of network shards process data asynchronously or completely out of sequential order, the final mathematical sum remains completely finite. This strict analytic limit completely neutralizes malicious transaction reordering attacks. An attacker shifting the execution timing of network participants simply cannot inflate or manipulate the final economic output. Relying on artificial user caps to maintain stability is a primitive approach to network design. An unbounded participation network naturally guarantees bounded, fair economic distribution when it operates on built-in mathematical decay curves. Turing-complete environments inherently suffer from the computational halting problem. Poorly coded logic can trigger catastrophic, infinite feedback loops that permanently freeze the software state. We eliminate this risk using the well-foundedness projection operator. This native constraint forces strict architectural boundaries directly onto abstract software logic. It explicitly confines all recursive processes strictly within the first uncountable ordinal hierarchy. If a dynamic system transformation attempts to execute an infinitely recursive logical sequence, the state machine instantaneously flags it. Because the proposed logic lacks a definitive termination ordinal bound, the system evaluates it as illegal, and the algorithm mathematically cannot compile into memory. Bounding digital architectures to well-founded hierarchies provides baseline security against paradoxical code. It renders permanent network freezes impossible at the structural level. The final vulnerability in decentralized systems is physical connectivity. Aggressively scaling a network often leads to structural fragmentation, where isolated node clusters detach from the global consensus state. To audit this connectivity, we use spectral graph embedding. We extract the raw node data of the entire network into an instantaneous algebraic matrix. This utilizes the graph Laplacian to mathematically separate where physical connections exist from how heavy the structural load is. We strictly enforce Ramanujan bounds on the network's spectral gap. By locking the eigenvalues within this limit, the system proves maximum expansion efficiency. This single algebraic check guarantees massive global structural resilience instantly. We do not need to run computationally expensive deep code scans to verify the network is intact. Binding physical connectivity directly to spectral eigenvalues engineers the possibility of isolated Sybil bottlenecks completely out of the enterprise architecture. We take these four standalone constraints, the fractal operator, Zeta aggregation, well-foundedness, and spectral graph bounds, and synthesize them into a single, unified execution layer known as the master theorem system. A state transition is only valid if it satisfies the master synthesis equation. The invariant of the transformed state must equal the original invariant, the Zeta aggregation must remain finite, and the logic must be bounded within the well-founded hierarchy. This framework is governed by admissibility algebra. Combining any two mathematically valid, distinct transformations will always yield an overarching state that is mathematically safe. If an adversarial attack violates just one of these parameters, whether by causing value divergence, triggering a structural shift, or initiating an infinite loop, it triggers an admissibility error and shatters at the compilation level. This is a departure from classical cybersecurity. We shift defense away from guessing probabilistically hard cryptographic keys, moving entirely into absolute, deterministic algebraic rejection. The network's true identity is the unforgeable structural invariant itself. Successfully compromising the network requires executing computationally impossible, paradoxical mathematics. To understand the scope of the extended TQFT framework, we have to establish its strict epistemological boundaries. There is a sharp distinction between analyzing genuine, dynamic quantum phases of matter and structuring static, abstract computer code architectures. This digital extension does not attempt to overwrite or replace established physical quantum field theory. Instead, it operates strictly as an effective theory for computational systems. It is a mathematically inspired abstraction that actively requires non-physical artificial boundaries in order to function. The strength of this architecture is that it systematically isolates the exact thresholds where physical geometry fails, installing numerical limits to stabilize infinite scalability. By translating topological invariance into Turing-complete algebra, we can mathematically guarantee that infinitely scaling a digital network requires absolutely zero loss of its core identity.